Hi, students. I hope you are well. We are looking at chapter 7, which is control techniques in experimental research. There you go. Alrighty, in this chapter, or this session, actually we have 2 chapters to deal with in this session. This first part, we will look at control techniques in experimental research. Control at the beginning of an experiment. Before we do that, how do we manage control, and then control during the experiment when you are busy with any kind of experiment. What do we do to control sequencing effects, participant effects, and experimenter effects? Remember, the last lecture was about validity, and internal validity dealt with all these issues that might confound the dependent variable. All right. Now, last week we looked at the Zoo-Spelker project. I just want to recap because we're going to base some of the principles again on this particular project. And as you can see, the background now is sort of yellow or orange or whatever. The red stuff is still not in the book, and you should know that, but the yellow slides, it's not in the book, and you don't have to learn this. Right, so you don't have to know the numerosity project, although I think it will be good if you remember the principles. All right, so the research problem can be divided in the question, variables, and relationship, and how do we assess those. Last we said the research question was, what is the effect of set ratio on infants' approximate numerosity sets, or ANS? Don't know what that is, go and watch the video, the last one. Variables in the relationship in this project was the independent variable was the proportion between set sizes or set ratio, which was 1 to 2 or 2 to 3. The dependent variable is the ability to identify small versus large number of dots, events, or objects, or what have you. Then, how do we assess those? The independent variable by me, sorry about that, I shouldn't do that. The independent variable is measured by the number of dots, and I'll explain that. The dependent variable is measured by gaze time, or how long a child or a baby looks at a particular presentation, and I'll explain that as well. All right, let's just go back to the measuring of the independent variable. The 2 ratio sets that we had was 1 to 2, and as I explained last time, there's a box or a presentation of 8 items and 16 items, which is a ratio of 1 to 2. Ratio of 2 to 3 is 8 and 12. All right, let's see here. They don't look much different, but in principle, and what was found empirically was that animals and babies cannot discern the difference between these, but the difference between those. All right. Then measuring the dependent variable, which is one of the most fascinating things about this project. Remember what I said about you don't know what the chicken thinks, except by observing him and making your own inferences, but you also don't really know what a baby thinks, except if you see the baby cry, laughing, blah, blah, blah. But there's they discovered a mechanism called habituation, which happens when a baby gets used to a particular stimulus. It works for animals as well. As soon as you get used to a stimulus, you do not attend to that stimulus anymore. So if you show a baby a novel stimulus over and over and over again a few times, he will sort of lose interest because he gets habituated or used to this, and the gaze time decreases. All right, and you can actually see and determine the point where habituation sets in when a certain level of gaze time is reached, whatever milliseconds that may be. All right, so this is an absolute fantastic way of assessing babies' intentions, interest, awareness of issues that they probably are not even aware of themselves. The object permanence video that I showed you in the first lecture uses this as well. Babies look longer at the situation where they expect something to appear, but it doesn't. All right, so that's how you know that there's something like object permanence involved. All right. Use exactly the same process to determine the choice between a smaller number and a large number. Gaze time diminishes when habituated or getting used to stimuli. In presence of novel stimuli, then the gaze time increases rapidly and significantly. Right, and they use this, or they use this particular fact to assess babies in this numerosity project. Now, remember as well, we said there were a number of confounding variables, and a confounding variable is an extraneous variable, but it confounds or influences the dependent variable. Object tracking, remember there was three ways of counting. The one is counting the objects or tracking the objects, or approximate number sense, which we are dealing with now, and subitizing, which is the automatic recognition of the amount of dots or whatever. In this instance, we would like to distinguish it from object tracking or discount that. And how can you control that? Well, basically by increasing the number of dots so that they cannot, for instance, track the number. And then they found that there were a number of display characteristics such as color, spacing, element size of the dots, differences in contour, which basically means the contours of the elements are larger in the one. So if you get larger dots, you get longer contours and so on. Brightness. Yeah. As you can see over here, the yellow dots are more bright than the blue ones. But also, for instance, in this display over here, the densely packed dots in a small space is less intense or bright than, for instance, this one, because there's lots of white space around there. The amount of dots, obviously, as you can see over there. The element or display density, similar to this brightness thing. How tightly packed it is in a particular display, and then the display size as well can influence them. The dependent variable, gaze time. Okay, so how do we control all of these as confounding variables so that they do not influence the dependent variable? That's the main question. All right, so they had one sample of babies, but they divided the babies into two groups. Why? There was two habituation groups. The one with the number of 8 dots, and one with the number of 16 dots. So instead of showing habituating the babies to both, which would be useless, they divided the sample into two and habituated a group of babies to the smaller amount until the gaze time decreased, and the other group they habituated to the large number of dots. And then both groups got the same test. All right, so the habituation exercise by showing them these was just for habituation, or getting used to the smaller amount or the larger amount. Now the expectation is, if babies are habituated to the smaller amount, as soon as you show them a display that has got more dots than that one, they should look longer, and the other way around. So two groups of babies, very clever, not only one group, two groups, each habituated to a different amount. So you can see whether there's an effect of the displays. Right. Okay, so now the slides have got this points of introduction, which you can read in the textbook. Important, what they say is random selection is rarely used. Researchers focus on the independent variable. Purposive and convenient samples typically used, which is not correct. If you would like to generalize, then you should actually utilize random selection. But as they say, as soon as you focus on the effect of the independent variable or the causal mechanism over there, then they decrease the generalization validity and increase the internal validity by specifically choosing, in experiments now, choosing samples that fit the criteria in which you can control certain stuff. That will become clearer as we go on. Right. And there's just another example of random sampling and random assignment. You should have that clear in your minds by now, that random selection and random assignment are two different things. They work on the same principles, but they have different purposes. Okay, we are dealing with this thing over here, random assignment, or the construction of my different treatment groups, which might include a control group. Right. The goal of experimentation, as you know by now, is to identify the causal effect of the independent variable on the dependent variable. Must have internal validity to do this, requires control. This is stuff that you know, and you should eliminate differential influence like the confounds. I'm not going to explain this. This is what we've done up till now. Right, random assignment is a control technique. That's why we deal with this. A control technique to equate groups of participants. And why is it important to have similar treatment groups? Think of it. Why do we need similar treatment groups? And I'll come to the answer in a second. Accomplished by ensuring that every member has an equal chance of being assigned to any group. Provides maximum assurance that groups are equal. So the first prize, my friends, are always random assignment. This is all too quickly discarded nowadays in experiments. and it has devastating effects on the strength of validity and the conclusions that you can make. You need to assign the groups or make sure that they are equal in some way. And if you can, you do random assignment. It eliminates systematic differences between groups, doesn't eliminate extraneous variables, but randomly distributes them across groups, and I'll show you how that works. There is a red slide, which is not in the book. Here's the same thing, a large population, which I randomly select, 12 people. And then I need an experimental group and a control group, and I need to assign them to both. Now, if you look at my two groups over here, look carefully. Do they look similar in terms of certain characteristics? And I'm not talking about race or hair length or something like that. Just look carefully at the pictures. The characteristics that might have an influence on the dependent variable are stuff like age. And you can see this is a younger group. This is a sort of an older group. There are older people involved here. Gender. 1, 2, 3. 1, 2, 3. Okay, they are equal in terms of gender. IQ, that we don't know. IQ is an example. It might sometimes influence your experimental outcome. Health status. We can see that if there's certain tasks to be done, somebody might, in the wheelchair, might have difficulty doing that. So there's a differential effect in the two groups. Language might have levels of aggression, which we can't see just like that. If you do an experiment where aggression is a confounding variable, you need to equalize the two groups. Why? Because if we've got more aggressive people over here, it influenced the dependent variable that we want to control. Thing like attention to detail. So for instance, we do an experiment where attention to detail is required. If we have a lot of sloppy people in the one group, but in the other group, for whatever reason, more attention to detail people, it will influence them. So we need an equal mix of characteristics. Numeracy skills might be one, levels of optimism might be another one. It all depends on what you would like to achieve with the experiment. So all the extraneous variables that I can't see or know about should be distributed equally between the different treatment groups. Control group is crucially important to have that equal to the other groups. Otherwise, there might be a characteristic that influences the outcome, and you cannot say it was a control group. Right. So there's an example of random assignment, which I'm not going to discuss. You can read that in the textbook. I think I've said everything that I need to say over there. Okay, students, you might pick up a little bit of a discontinuity problem. Blame that on load shedding. So I had to sit in another venue with a little bit of a different acoustic and background. So in any case, let's kick off with matching again. The first way of equalizing groups is through a random assignment. Second one is matching. You can use a variety of techniques to equate participants in the treatment groups on specific variables. This should be done with variables thought to be related to the IV or which may confound the IV. We know by now what a confounding variable means. So if we have, let me just go back to that previous one. If we have something like gender that might influence the two groups, we can use gender as a matching variable. All right. Advantages of matching is it controls for the variables on which participants are matched, and it increases the sensitivity of the experiment for that particular variable. Okay, holding variables constant is another way. Let's use this gender example and see how we hold gender constant as a variable. If we do a study on conformity issues and gender and so on, we probably would like to use only females. Look at the right-hand side. We have our population of all people, includes both males and females, but for this particular study, we are going to draw a sample of only females to control for the influence of gender. Do you understand why we include only females? Because if we include males, we may get biased results. We would like to find out what females think and not bias it with the opinions of men. All right. If possible, sample of females randomly assigned to treatment conditions, whatever that may be, treatment A, B, and C in a control group, but the point is the groups consist totally of females. The disadvantages is it restricts the population size, of course, and it restricts generalization to other types of participants. But of course, you are interested in holding the effect of gender constant, which means controlling it. All right. Next technique, building the extraneous variable into the research design, and we call this blocking. It's an important concept to take note of. Basically, you make the extraneous confounding variable another independent variable. And in that way, you control its effect. Should only be used when you are interested in the effect of this particular extraneous variable. Let's look at this example, which comes out of the textbook. We have a sample of participants with IQs between 90 and 119. We have a subsample with specific IQ values identified, and that is, in other words, the blocking variable. You include one subsample or group with participants in that range, participants in the range of 100 to 109, and then there's almost 10 IQ points difference in each, and they are not overlapping. So in this way, you can control the effect of IQ on whatever you are studying over there. And in this instance, it is learning strategy. So the level of IQ is then used as a blocking variable. Right. Third one, yoked control. You know what yoked means? It means grabbing someone by the neck, pulling them out of something. You match participants on the basis of the temporal sequence of administering an event. So An example is a research question. A researcher wants to know the effect of students having the freedom to choose snack breaks on their classroom productivity. And each control participant is yoked or attached to an experimental participant. So as soon as the experimental participant in class, for instance, says, I want to have a snack break, then the control attached or yoked participant is also given a snack break by the teacher, and you can do whatever measurements you want to do. Just understand the issue of matching in terms of these different strategies. All right. Matching by equating participants. This is very popular and a useful method to do equating. You match case by case and randomly assign them to groups. The advantage is that groups are equated on potential extraneous variable. Disadvantages is identifying the variables on which to match. Matching participants increases as the number of variables which to match increases. So that's the more variables you identify, the more difficult it is to match. And some variables are difficult to match in any case. And like all matching, it decreases the generalizability of the results. All right. Let me use an example. That particular example, you can read through it each. We have a sample of research participant. Each participant measured in terms of age, gender, IQ, and so on. Each participant is matched with second participant of same age, gender, and IQ. That provides many matched pairs. If possible, participants in each match pair are randomly assigned them to. Let's look at the example. Let's match these guys, the sample on IQ. So you can see Sarah has got an IQ of 110 and Brian. So they make a pair. Now, which one goes to the control group and which one goes to the treatment group? You do that randomly. First match and then assign the one randomly to either the treatment or control, and then the other one goes to the opposite one. Same with Jane, 95, and Kathy, 95. Then randomly assign. And can you see what the effect is? You keep the effect of IQ on the group constant because the average IQ of the left-hand side and on the right-hand side will be the same. So IQ cannot have a differential effect. Right. Now that is measures that deals with equalizing groups. Now we're within the experiment, and there are a number of threats to validity within the experiment as well. And one of the major threats is when you have repeated measurements on the same person over time. Counterbalancing is one method to alleviate the problem of bias when using repeated measurements. All participants should receive all treatment conditions. There should be another L over there. All right. Yellow slide, just an example. Do not panic, you don't have to know this for the test. I would like to do a test on a number of normal functioning adults to see to what extent they experience the phenomenon of pseudo-neglect. Now, do you know what pseudo-neglect is? It is the natural tendency to perceive things a little bit on the left in normal adults. With adults or children with certain brain lesions and so on, tend to experience neglect on the right-hand side. So they cannot perceive, or they do not focus on the right-hand side, or they focus on the right-hand side rather than the left. Pseudo-neglect means it's not a real major issue, but normal adults tend to estimate or focus their attention a little bit to the left of the center. It's got interesting implications for a number of things. Now, one of the ways that you assess for pseudo-neglect is to give people, or neglect in any case, is to give people the line bisection test, or the LBT. Consists of a sheet with a number of lines, and you ask a person, listen, indicate the exact half of that line. Bisect the line with a pencil in some way. And as you can see, some of the lines are left, some of them are right, some of them are long, some of them are shorter. So they go through this. And what happens is that we measure the deviation from the center, whether it's left or right, to see whether pseudo-neglect is visible or actual neglect. Right. Now, what is interesting is that with this type of test, it's a sort of a neurological tool to determine whether people are experiencing serious brain damage or neurological issues. But some research has been, well, actually quite a lot has been done on a number of aspects of the line bisection test. And as you can see, as I've said, some lines are long, some are short, and those might actually influence the extent of pseudo-neglect. And one of the fascinating research projects or research that has been done was to see whether you tend more towards the left using your opposite hand, your left hand if you are right-handed, and the other way around. So some research has been done about that. But in any case, so my question is, does line length influence pseudo-neglect of normal functioning adults? And all that I would like to check then is whether a short, medium, or long line like these would elicit more or less pseudo-neglect to the left. All right, so I've got three options, three questions that they need to answer, A, B, and C. Now, these three conditions are applied to each participant. It might be that if you get the long line first, it influences your response on the next one, and so on. We don't know. So it is better if there's a sort of a carryover or a sequencing effect to randomize the order of presentation so that each subject gets a different order. All of them in the end will get similar orders, but we would like to counter the effect of giving the long one first versus the short one, and so on. All right. Another example which comes out of the book. If you would like to expose a participant with anxiety or what have you, or depression, to 3 types of treatment. Client-centered therapy, which is A, rational emotive therapy, or Gestalt therapy. The one way to actually do that is expose each client or participant to all 3 consecutively. But now you can understand, if I start off with client-centered therapy, that might be a carryover effect towards the next one. So we would like to counter the effect of the order of the therapies by mixing this up. Right, come back to this. Counterbalancing is used to control sequencing effect. Now, a sequencing effect, or there are 2 types of sequencing effects. The one is an order effect. It's a type of sequencing effect arising from the order in which the treatment conditions are administered to participants, which may lead to them practicing and getting better over time or experiencing fatigue. Then there might be carryover effects as well. It's a sequencing effect that occurs where performance in one treatment affects performance in another one. And that's what I referred to over here. The same goes for that one. Right. Now, counterbalancing procedures can be divided in a number of types. The first one is a randomized counterbalancing. The sequence of conditions is randomly determined for each participant. If I have an independent variable with 3 levels, as we have in our 2 examples, there are 6 possible sequences. Can you see? We've got ABC, ABC, and the order can be ABC, ACB, BAC, all right, for both the line bisection task and therapy. Each participant is then randomly assigned to one sequence. Well, it's easy in that example to do that. You can even do it with that. But now in this type of thing, you would like to do more than one trial. If a trial consists of 3 conditions in a particular order, I would like to, for instance, have 10 trials and average those trials. So in this instance, you would expose each participant to a long sequence of orders. But in the therapy one, we'll assign one participant to each order. All right. Complete counterbalancing means that you are, like in that particular instance, all possible sequences. But the problem is, as soon as you go over 4 levels of treatment, then it becomes really, really tough. We use a formula, which you need to know, called n factorial. It is n multiplied by each number below it. Like for instance, if we have 2 levels, we put it into that formula. 2 factorial means 2 times 1 equals 2. So there are 2 conditions, AB and BA. 3 factorial is 3 times 2 times 1. You get the idea. And the total is 6. So we have 6 possible sequences. Now watch what happens. As soon as you get to 4, you get 24. And so on. So it increases exponentially. So it's really difficult to do complete counterbalancing over 3 levels in any case. All right. But Counterbalancing with 2 and 3 levels can be done fully. Incomplete counterbalancing doesn't, as in the previous instance, utilize all of them, but some of them, which is relatively randomized and sort of has the same effect. Most commonly used technique, not all possible sequences are used. The criteria for sequences enumerated. Each treatment condition must appear in an equal number of times in each ordinal position, 1, 2, and 3. 4. Each treatment condition must precede and be followed by every other condition an equal number of times. So here's the formula, and I'll explain it to you. You use the formula up to the correct level. If you have 3 levels, you use it up to 3. If you have 4 levels, you use it up to 4. If you have 5, you use it up to 5. Then you replace the values, and I'll show you how that works, and then you start the next sequence by increasing each element by 1. Let's look at an example. If we have 3 levels, we'll use the first part of the formula, 1, 2, n, 3. So n, 4 levels. 1, 2, n, 3. So it's 1, 2, 4, 3 is the numerical sequence. And if you replace that with your A, B's, and C's, it's A, B, D, C. And then you increase each one. A becomes a B, B becomes a C, D falls back to A again, and C becomes D. And you carry on like that for all the participants, and you get a sequence like that. All right, let's do one more with 1, 2, 3, 4, 5. Levels. All right. 5 levels. So it becomes 1, 2, 5, 3, and then n minus 1, which is 5 minus 1 is 4. 1, 2, 5, 3, 4, and replace that. It's A, B, E, C, and D. And increase it for the next one. A becomes B, B, C, E falls back to A, C, D, and D, E. And carry on like that for the whole sequence of participants. Right. Now differential carryover. The treatment condition affects participants' performance in a later condition in one way and another way when followed by a different condition. So it's just the order that actually has an influence. An example is the carryover from treatment A to 4 is 4 units when it's immediately followed by treatment B, but the carryover for treatment A is 2 units when it's by C. So if you suspect something like this, you shouldn't use repeated measurements. It's very difficult to, if you can have an influence like this to control it. All right. Then, now you've seen we've got the quality of groups, threads, sequencing threads within the experiment, and now we look at the participant. And that's easy. The participant effects is variables that you as a participant bring to the experiment. And the double-blind placebo method is neither the experimenter nor the research participant is aware of the treatment condition. So both are blind. Both do not know who's what and going on. You can also use deception when doing experiments. Right. How do you control participant interpretation of an experiment? Because how I interpret or think about or stuff that I expect can actually influence my reactions in the experiment. These are techniques used to gain insight into participants' perceptions of an experiment. You can do a retrospective verbal report, which is you ask them afterwards, what did you think about the experiment? How did you experience? Blah, blah, blah. And there are the questions. You can also do concurrent verbal reports while they are busy doing those experiments, and there are a number of techniques that you can use, which is quite simple to understand. You can also control, now we're with the experimenter effects. First, the participant, now the experimenter. You have to control recording errors because I, as the experimenter, can do that. Make researchers aware of making careful observations and so on. Use multiple data recorders and have participants make responses on the computer and so on. Now, control of attribute errors refers to the attributes of the experimenter. And these might be stuff like experimenter expectancies. You can use the blind technique, partial blind technique, or automation to control experimenter expectancies. Now, what is the experimenter expectancy? It's when I expect a certain outcome, and with non-verbal information, we did this with the threats. With non-verbal information, I can sort of influence the participants, and these are ways to control for that. Okay, we'll go over to the next chapter in a second.